There are two objectives in this section. First, determine intervals on which a function is increasing or decreasing. Apply the first derivative test to find relative extrema of a function. You will learn how derivative can be used to classify relative extrema as either relative minima or relative maxima. First, it is important to define increasing and decreasing functions. A function f is increasing on an interval when, for any two numbers x1 and x2 in the interval, x1 less than x2 implies f(x1) less than f(x2). Look at this graph. For the first statement, x1 less than x2, we say this one is x1 and this one is x2, implies fx1 less than fx2. So for this point, the output is fx1. So we say here. And this point is less than fx2 point. fx2. So here's the point. And just say I connect these 2 points. So we can conclude this function is increasing. A function is increasing when, as x moves to the right, its graph moves up, and is decreasing when its graph moves down. For example, the function below is decreasing on the interval from negative infinity to a. Okay, so here is the interval from negative infinity to a. This is a point and is constant on the interval AB. This is the interval AB and this is a B point and is increasing on the interval from B to infinity. And look at the slope. The derivative is related to the slope of the function. In this interval, the slope is negative value. And in this interval, the slope is 0. And in this interval, the slope is positive value. As shown in theorem 3.5 below, a positive derivative implies that the function is increasing. A negative derivative implies that the function is decreasing. And a zero derivative on an entire interval implies that the function is constant on that interval. Let f be a function that is continuous on the closed interval AB and differentiable on the open interval AB. First, if f prime x greater than 0 is positive value, for all x in open interval AB, then f is increasing on closed interval AB. If f prime x less than 0 for all x in open interval AB, then f is decreasing on closed interval AB. Lastly, if f prime x equal to 0 for all x in open interval AB, then f is constant on closed interval AB. Find the open intervals on which fx equal to x cubed minus 3 over 2x squared is increasing or decreasing. Note that f is differentiable on the entire real number line, and the derivative of f is rewrite the original function and we differentiate the function. To determine the critical numbers of f, set f prime x equal to 0. We factorize the 3x and we solve for x. So we obtain critical numbers. Since we have two critical numbers, 0 and 1, so look at these 2 points, 0 and 1. So from these 2 points, we can distribute to 3 different intervals. So the first interval is from negative infinity to 0, and the second interval is from 0 to 1, and the third interval is from 1 to infinity. Then immediately we construct a table like this. The first row we name it as interval, second row test value, third row sign of f prime x, and the last one is conclusion. So for the test value, we select any value from this interval. For example, -1. And for this interval, between 0 and 1, we select half, any value, as long as within the interval. And for the third interval, 1 to infinity, we choose 2. And then we substitute this test value into the f prime x function. And we have the value is positive 6, is greater than 0. And for the second interval, the f prime half is negative value. And for the third interval, f prime 2 is 6 positive value. So based on the theorem, we can conclude for the first interval, the function is increasing. And for the second interval, the function is decreasing because negative value. Then for the third interval, since the value here is positive value, so the function is increasing in this interval. Now look at the proof. The interval from negative infinity to 0 is increasing. And for the second interval, 0 to 1, the curve is decreasing. And after 1, the curve is increasing. Example 1 gives you one instance of how to find interval on which a function is increasing or decreasing. The guideline below summarizes the steps followed in that example. let f be continuous on the interval ab. To find the open interval on which f is increasing or decreasing, use the following steps. First, locate the critical numbers of f in open interval ab, and use test numbers to determine test intervals. Determine the sign of f prime x at one test value in each of the intervals. Use theorem 3.5 to determine whether f is increasing or decreasing on each interval. Test guidelines are also valid when the interval of the open interval AB is replaced by an interval of the form from negative infinity to b, from a to infinity, or from negative infinity to positive infinity. A function is strictly monotonic on an interval when it is either increasing on the entire interval or decreasing on the entire interval. For example, the function f(x) equal to x cubed is strictly monotonic on the entire real number line because it is increasing on the entire real number line. The function shown in figure below is not strictly monotonic on the entire real number line because it is constant on the interval from 0 to 1. After you have determined the interval on which a function is increasing or decreasing, it's not difficult to locate the relative extrema of the function. For example, in this figure, the function has a relative maximum at the point 0, 0. Because f is increasing immediately to the left of x equal to 0 and decreasing immediately to the right of x equal to 0. Similarly, f has a relative minimum at the point 1, negative half, because f is decreasing immediately to the left of x equal to 1 and increasing immediately to the right of x equal to 1. Let C be a critical number of a function f that is continuous on an open interval I containing C. Look at the figure here. This point is a C point. If f is differentiable on the interval I've set possibly at C, then fc can be classified as follows. If f prime x changes from negative to positive at C, then f has a relative minimum at CFC. For example, for the first diagram, this point is relative minimum because the slope, the f prime x, the slope changes from negative. The slope here is negative. Change to positive at C. So we say this point is relative minimum. For the second, if f prime x changes from positive to negative at C, look at this figure, then f has a relative maximum at C, FC. This is a point. The slope changes from positive to negative. For the third, if f prime x is positive on both sides of C, or negative on both sides of C, then FC is neither a relative minimum nor a relative maximum. Look at this figure, and this is the point C. The slope on both sides is positive. Or look at the point C for this curve. The slope here is negative. And for this interval, the slope also is negative. So that's why for this two figure, we conclude neither relative minimum nor relative maximum. Find the relative extrema of the function in the interval from 0 to 2 pi. Note that f is continuous on the interval from 0 to 2 pi. This is a given information, the interval. The derivative of f is f prime x equal to half minus cosine x. To determine the critical numbers of f in this interval, set f prime x equal to 0. And to get the x, we move the cosine to other side, so will be cosine half. And the x value are pi over 3 and 5 pi over 3. Same for the previous example, since we have 2 points, so we will have 3 intervals. For the first interval is from 0 to pi over 3, and the second interval is pi over 3 to 5 pi over 3, and the last interval is 5 pi over 3 to 2 pi, because the given interval is from 0 to 2 pi only. And for the test value, select any value from the respective interval. And we substitute into the f prime x function. And based on the sign, we conclude the answer. For the first interval, the sign is negative value, is negative, so it's decreasing. And for the second interval, the sign is positive, so it's increasing. And the last interval, the sign is negative, so it's decreasing. By applying the first derivative test, you can conclude that f has a relative minimum at the point where x equal to pi over 3. So look at this point. This point is a relative minimum because the slope changed from negative to positive. And we say this point is a relative maximum because the slope changed from positive to negative.